Aberrations are imperfections in optical systems and components that contribute to adulterations in the final image. There are numerous types of optical aberrations, and a couple of them are explored in this lab. Wavefront error is a measure of how closely the actual wavefront shape is to an ideal wavefront or reference sphere, where rayfan error is a measure of how closely a ray is to its ideal image point. Each type of aberration, such as tilt, defocus, and spherical aberration, has its own equation for calculating the corresponding wavefront and rayfan error. These equations are dependent on normalized Cartesian or polar pupil coordinates. Defocus and spherical aberration specifically are dependent on pupil location and independent of field. The goal of this lab is to explore spherical aberration in a specific test lens.
Spherical aberration is a consequence of the spherical shape of optical components such as lenses and creates error in the direction the rays passing through a lens refract. Namely, the marginal and paraxial rays don't focus in the same plane, creating a paraxial mid and marginal focus, which is defocused from the paraxial focus at a distance known as a longitudinal aberration as seen in this slide. This makes characterizing spherical aberration at a paraxial focus, which is the ideal image plane, using a physical rayfan, difficult. It is easier to characterize spherical aberration measuring a physical rayfan at the marginal focus. Spherical aberration at paraxial focus can be measured by taking the rayfan at marginal focus and subtracting the measured defocus term. The rayfan diagram shown in this slide is the ideal shape of the rayfan diagram at the marginal focus. The spherical aberration error term gives the peak and trough in the plot, and the defocus term is linear, which gives the slope towards the center of the plot. When working with just a thin plano-convex lens, the largest contribution to spherical aberration from the lens is from the shape of the lens and the orientation with respect to the beam. These are taken into account as the shape factor B and the conjugate factor C. When calculating the spherical aberration in a thin lens, we know that the conjugate factor will be -1 since the object, or the laser beam, is at infinity. We predicted that the positive shape factor should be at about 0.71, and that would result in minimal spherical aberration, which means that the light should be incident on the convex surface, as it is a positive number.
A Hartmann mask allows for us to essentially be able to control where a ray will pass through the pupil coordinates of an optic. Thus we can go from being in the center or any normalized position all the way up to the marginal ray of the optic. We measure the ray aberration by using a Hartmann mask and a pentaprism. The pentaprism would guide the beam by turning it at a 90-degree angle, guiding it through different holes on the Hartmann mask. Once through there, it would pass through the optic that we were testing and then be focused and imaged on a microscope. And through that microscope, we could then see where the ray would transfer onto image plane. The first part of this lab, after alignment was done, was to find the marginal focus of the lens. This was done by putting the pentaprism at an extreme such that we were passing a marginal ray through our lens. Once we had the marginal rays on focus on the microscope, we were then able to image it onto our screen. Then we were able to translate our pentaprism across the Hartmann mask, such that we were getting points across the normalized pupil position based on that mask. Through that, we were able to see the spherical ray aberrations on the image screen.
As shown in the graphs, our proportional rayfan diagrams measured in part C turned out well, but our rayfan diagram measured in part D showed measurement error. Due to time constraints, we didn't get to part D in the plano-convex orientation.
The next step was to find the paraxial focus and the longitudinal ray aberrations. This was done by translating the pentaprism such that the beam was traveling across the Hartmann mask. While doing so, we were translating the Z positioning of our microscope such that it kept the center position of the spot on the center of our crosshair from the original image. While doing this, we were using a translation stage that did not have a micrometer measurement tool on this stage. This was because we were running out of micrometer stages in lab and had to borrow one from a different lab. To manage this, we measured each position using a ruler to get the difference between the microscope objective and the lens position.
Due to not having a precise measurement tool, our results were not ideal.
The initial laser alignment proved to be more difficult than expected. When introducing the pentaprism, the deviated beam no longer fit through the pinhole due to the elongation of the optical axis and the innate beam deviation of the laser. Therefore, the farther the beam travels, the more the beam deviates. We also had issues aligning the microscope reticle with the laser beam because the microscope post was initially loosely attached to the microscope holder. This caused the rotation in the microscope post when making the fine adjustments. We fixed this by changing the microscope post and making sure the movement to the fine adjustments were performed. Due to time constraints, the proper reticle alignment was not obtained. However, we were able to align the microscope such that the beam on the screen was at the original location prior to inserting the lens and microscope. The position of the crosshairs was adjusted to the best of our ability to be in close proximity of that spot.